Last time we turned text into the enemy and beat it. We built a tokenizer so every character now has a number, an ID. But a number is a name, not a meaning. To the model, token 5 and token 50 are just labels. Today we give each ID a body, a little vector of numbers the model can learn, and then we go get a real book to feed it. So here's where we are. We have a string of token IDs 18, 47, 56, 57, useful for bookkeeping, useless for thinking. The model can't multiply an ID and get anything meaningful. We need to turn each ID into a vector, a row of numbers that can carry meaning. That's the whole job of this episode's first tool. The tool is nn.Embedding. Picture a table, one row per token in your vocabulary, and each row is a vector of length n EMBD. Token I just looks up row I. That's it. It's a lookup table. The twist is that the numbers in that table aren't fixed. They start as random noise and they get learned during training, nudged a little every step. Why not just feed the IDs straight in? Because integers lie about order. ID 5 is not less than ID 50 in any meaningful way. H isn't half of P, but a network doing arithmetic on raw IDs would treat 50 as 10 times bigger than 5. Embeddings break that false ordering. Each token gets its own independent vector, free to mean whatever it needs to mean. And here's the beautiful part, meaning becomes geometry. As training runs, tokens that behave alike drift toward nearby points in this vector space. The old way, one hot vectors, was a wall of zeros with a single one, sparse, rigid, dead. Embeddings are dense and alive. Every number is doing work and every number can move. Now the shape story, because shapes are how you debug PyTorch. You hand the embedding a batch of integers, shape BT, B sequences, each T tokens long. Out comes BTC, same grid, but every integer has bloomed into a C-long vector. We added a depth axis. That third dimension, the channels, is where all the meaning lives from here on. Okay, we have the machinery, now we need data and not 3 toy sentences. This is where Hugging Face Datasets earns its keep. Load dataset pulls a curated public corpus in one line. We'll grab Tiny Shakespeare, the plays over 1 million characters, downloaded and cached. It actually arrives pre-cut into train, validation, and test splits, so our very first move is to glue those 3 back into one continuous book. Why glue then recut? Because we want to own the split. We stitch the splits into one long string, encode every character to its ID, and concatenate it into a single tensor. One stream of 1 million plus integers, then we cut it ourselves. The first 90% is training, the last 10% is validation. We never train on the val slice, it's the honest exam. The only way to know if the model is learning or just memorizing. B0 overview. Here's embed data.api. Top to bottom, imports, then load the corpus and stitch the splits, report its size, build the chart to ID maps, encode the whole thing into one tensor, split it, and finally demo the embedding on a small batch so you can see the shape change with your own eyes. 2 pages, let's walk it. Imports first, torch and torch, nn for the embedding, and load dataset from datasets. That datasets import is the new phase today. It's the library that puts thousands of public corpora one function call away. Load and stitch. Load dataset, Karpati, Tiny Shakespeare, trust remote code, true. Returns a dataset with 3 splits. It ships a tiny loader script, which is why we pass trust remote code, true. Each split holds the text in a single row, so we pull the 3 text rows and join them back into one continuous corpus. Then we print the character count, 1115 of 394, so we know the download worked before we trust anything downstream. Always sanity check your data's size first. Build the vocabulary. We take the sorted set of unique characters, that's our vocab. Story maps each character to an integer, ethos maps back. Same character level scheme from last episode, just rebuilt on the real corpus, 65 unique characters this time. Encode the whole corpus. Encode is a one-line list, comprehension over story. We wrap the result in a torch, long tensor. Now the entire million character play is a single 1D tensor of IDs, one continuous stream. The train to val split, we slice at 90% of the length. Everything before is train data, everything after is val data. One line, but it's the line that keeps you honest. The model never sees the val tail during training. Now the embedding itself. N0 embedding vocab size NEMBD. Vocab size rows, each NEMBD wide, with 65 unique characters and 32 dimensions. That's a tiny 65 by 32 table of learnable weights. This is the lookup table from Act 1, made real. The demo batch. We grab a small 4x8 slice of token IDs, 4 sequences of 8, run it through the embedding, and print the output shape 4, 8, 32. The integers became vectors, exactly the shape story from earlier. Then, to see one row directly, we look up a single token, ID 46, and print its 32 number vector. That's a real row of the learnable table. Closer, B8 plus teaser, and there it is, BT integers in, BTC vectors out, riding on a real corpus. But a stream of IDs isn't training data yet. We need to chop it into input windows, and the next token targets the model predicts, and the model still has no idea what order the tokens came in. Next time position and the training batch, that's PT11.